In this presentation, we will encounter for the first time a fundamental complexity barrier that makes it difficult for us to implement the methodological principle I introduced in the second presentation. And this will lead us eventually to the adoption of the computational tools and techniques that will be introduced in subsequent presentations. But because this is so important and quite fundamental issue, I will go through this argument in a step by step. And the first step is that we recognize that human linguistic behavior, the expressions we create and understand and comprehend, are based on some type of combinatorial system. So if you look at some simple sentence like the dog bites the man, we could have a theory where this sentence would be memorized and retrieved from the memory when the occasion prompts it. And we could imagine that all our linguistic behavior would be based on this type of memorization or memory retrieval. But it's easy to see that that's not the case, that sentences like this and other expressions are formed somehow by creating them by combining smaller units. In this case, I depicted this sentence as being composed by combining or concatenating words. The followed by dog, followed by bites, followed by the, followed by man. So I'm putting these words together in a sequence. And it's easy to see that we can create an arbitrary amount of new expressions by, for example, changing the ordering of the words. So we can say the man bites the dog simply by shifting the positions of these two words. And in this way, we can create new expressions creatively. We can, for example, we can add adverbial modifiers, such as the man bites the dog if he's crazy. So we are combining two sentences, and there is virtually no limit in the complexity of expressions that we can create, and no limit on the permutations and different permutations we can create from some set of words, as long as they follow the rules of grammar. So that's the first observation we have to make. Language itself is fundamentally, and underlining it, there is a combinatorial system that is able to create new expressions by combining more primitive, more smaller units, ultimately the words. But that's not all. We can also make a simple experiment to demonstrate that this concatenation model that I'm illustrating here, where we imagine that the sentences are just sequences of words and that the combinatorial operation is simple concatenation, where we put words into linear order. We can show that this model is insufficient. And to do that, we can take some simple sentence like, I saw the girl with the telescope. And it's easy to notice that this sentence and many others like this sentence are structurally ambiguous. There are two ways to understand this sentence depending on how we analyze the preposition phrase with the telescope. One interpretation, and the one that comes to my mind first when I read the sentence like this, is that I'm looking through the telescope. And then I see a girl, perhaps because the girl is so far that I don't see her otherwise. So in that case, the preposition phrase with the telescope modifies the verb. It explains how I'm seeing something. But there's another alternative interpretation, which is that I'm seeing the girl and the girl is there with the telescope. So in this interpretation, the preposition phrase somehow modifies the object of my seeing the girl. And we can express this Well, first of all, notice that we are looking at the same sequence of words, same concatenation, same linear sequence, yet the linguistic expression, this same sequence has two structural, or could be also purely semantic interpretations, depending on how these words are structured together. And here is a way of seeing it. I just wrote these different structures more explicit. We don't need to pay attention now what these brackets are really about, just to make this point. So the first interpretation shown here in the first line would be so that I saw the girl, that's something, and then with the telescope modifies that event of seeing. It explains the manner I saw the girl. But here in the second interpretation and second line, with the telescope is inside the object because it modifies the girl. In the same sense as I would say I saw the girl from London. So then it's more clear that the from London is actually, it's a preposition phrase which modifies the object of the girl. So what does this all mean? It means that it's not only the case that language is a combinatorial system and creates new expressions by combining words or other primitive elements, but it's also, there is also a kind of hierarchical structure behind sentences. It's not just concatenation. Now, what this hierarchical mechanism is, how it works, how the brain is implementing it, that's an empirical question. We can't find out simply by looking at simple examples like this. But what I want to establish here is the simple truth that there must exist some type of combinatorial, hierarchical and combinatorial system that can create structures like this. And then the actual sentence, the concatenation, the words as they are in a linear sequence, as they are when I'm producing language or spelling out language, they are created by a separate mechanism that takes these structural representations or elements as input and then linearizes them into a linear order. And here it's just the case that these two structural representations, the first and the second, they create the same output, the same linear sentence. And that's why the sentence itself must be ambiguous. Now linguists and many theories, I would say all the plausible serious linguistic theories that have a chance to satisfy the sufficiency and necessity conditions for trivial data sets, they assume that something like this happens where we take more primitive or smaller elements, in this case the constituent representing the definite article, and then the constituent representing the noun, and we put them together, we merge them together or assemble them into a larger unit. And then this larger unit, the DP, can be exposed to the same operation. We can create ever larger units by continuing this combination. So we can then take this DP, for example, and combine that with verb such as barks. So we could have a sentence like the dog forms a complex unit, its own unit, which is combined with the verb, we get the dog barks. And the way how these combinatorial operations or assembly operations are performed will then create us structural ambiguities, as I just illustrated. So virtually every linguistic theory has something like this underlining it, and this example already alone shows that we can't really seriously capture interesting data, linguistic data, unless we have something like this in the theory or hypothesis. Now, one more point is that, of course, because I already made a distinction between attested and unattested expressions, we have seen already many examples of this distinction. And we also have to have a theory which captures this distinction, because our interest is in human linguistic behavior and human languages. And so we also have to assume that there are some limits on what type of elements this assembly operation can combine. For example, it's probably the case that this type of combination where I combine two definite articles, the and the, is not well formed. It's blocked, or something prevents it from happening. So sentences like the dog are not well formed, are not attested. English speakers can only use one definite article per noun phrase. And you can easily imagine similar restrictions. It's easy. And restrictions like this has to play some role in ruling out some of the unattested sentences, linear sequences of words. And okay, now we can just ignore the question of what type of rules these actually are. All we have to assume is that our hypothesis or theory of grammar must have some restrictions on how this assembly operation works and what type of constituents or elements overall it can combine with each other. And there are many more abstract restrictions. For example, we can ask, can we combine more than two elements? What about three? What about arbitrary amount of constituents? Can we have just one element? Can one element form a new complex constituent? And so on. Later in this presentation, I will go into more detail on how the theory of phrase structure, as it's called, can be implemented. But now we don't need to pay attention to it. Now I come to the main point. Let's go back a few presentations again. We noted that in order to satisfy the methodological principle, which requires that we show that the data follows from our hypothesis. And in this data set, we already have seen examples of both attested and unattested sentences. And so now the question arises, let's assume that that the data has this type of underlying hierarchical and combinatorial essence. In other words, we had to model the sentences in a datasets as generated by applying the assembly operation and possibly many other operations into the linguistic representations and elements, ultimately the words. In other words, every sentence is a result of an assembly operation, plus possibly many other operations that the grammar will require. For example, think about the second position clitics we just examined. Are they created by the same assembly operation than when we combine two words and they are two separate words? So you might perhaps think maybe there is another type of assembly operation or two types or even more. What I'm saying is that I'm using this example of assembly operation now to stand for any kind of operations or mechanisms or derivations you need to capture this data set. So we are now thinking already of calculating this data. That's what I'm saying. Remember that we will also have the linearization part of this model. So when we create these hierarchical structures, there will also be a linearization as an additional operation that will create the actual linear sentence. Now, if you have an attested expression in your dataset, how can we prove or demonstrate that our model predicts its properties and its existence correctly, or predicts that it is attested? One answer to this question, the simple one, and the one that most grammars today assume, is that we have to derive the sentence from the model or hypothesis by performing these assembly operations that are required to produce that precise sentence, plus the linearization. So we take the primitive elements from that sentence, and we then have an algorithm, or perhaps not even algorithm, but let's imagine we do this with the paper and pencil and notebook. We check that it is possible by taking those elements and by applying these precise operations in our theory exactly as they are defined. Remember that everything is now unambiguously defined, so we know exactly what these operations are. We start from the primitive elements, we apply them in some sequence, and ultimately we come up with a hierarchical representation which provides, when linearized, that exact same sentence. And that's the proof or demonstration that at least that one sentence follows from the hypothesis. But what do we do with the... So that is just the demonstration for one attested example of expression. In the reality, of course, we have to show the same sequence for every attested expression in the dataset. For example, every 45,000 words that I had in the dataset I just illustrated. But let's put that question aside for a moment and ask, but what if the expression is unattested? So it's some kind of a sentence where the agreement is wrong, or the critic is wrong, or the word hosting the critics is in the wrong place, or the negation is in the wrong place, whatever. What do we do? How do we show that the hypothesis does not correctly predict that that sentence is not possible? Well, taking the model, the starting point I just assumed, we have to again take all the primitive elements from that sentence or expression, and then we have to start creating the assembly operations. But if the sentence is attested, then the theory or model, it should not generate that expression, right? Because we require now that the unattested expressions are predicted not to be possible by our theory. So what do we do? Obviously, if we can derive it, then our theory has to be wrong. But let's say that we start to try to do in the notebook and paper and pencil, we start trying this derivation, and okay, we do a couple of those and we find, okay, now I was not able to get that sentence from the model. Should we conclude that the model is correct? Of course not, because perhaps if I try some alternative way of assembling the words or applying the operations, I could actually create that sentence. So to show that the unattested expression in the dataset is correctly predicted to be impossible by the hypothesis, we actually have to try every possible way of deriving expressions from that set of primitive elements, every possible way, and then demonstrate that whatever we try and whatever we do, that output sentence cannot be generated. And we can take the same logic now and apply it to the first example where we have an attested expression. Namely, we can use the same mechanical way of systematically trying every possible way of deriving sentences from the primitive elements until we generate the sentence in the dataset. And in fact, we have to go through every possible derivation, because if the sentence is ambiguous, like our example earlier, in that case, we also have to generate both meanings and both syntactic structures, or even more if it's ambiguous in several ways. And in order to generate them all, we can't stop the exploration of the possible derivations after we find the first solution. We have to continue until everything is explored and exhausted, and then we simply list all the solutions that were found. So in this way we would eventually be able to detect these two solutions. So in conclusion, to satisfy the methodological principle, for one attested or unattested expression in the dataset, we will have to calculate through every possible way of deriving hierarchical linguistic representations or phrase structures or semantics or whatever it is from the primitive elements that are in those expressions. And the problem is that because the system is combinatorial, the amount of calculations that is required is increasing exponentially as a function of how many words we have in how many primitive elements, let's say words, we have in this expression. The amount of different combinations and derivations we have to try is enormous. What I'm talking about, what kind of numbers? Well, we are talking about easily hundreds of millions of calculation steps. And when we are approaching this kind of, hundreds of millions of calculation steps, even for expressions that look like normal human language, are not very long or anything, like 10 words, for example, 11 words. And the combinatorics of this problem are such that if I have a 100 million calculation steps to find out if some expression is correctly predicted to be unattested, some one expression. If I add just one word to that, we get into billions of steps. The number increases so dramatically. This is simply mathematics. I have one paper, not yet published, but I did the experiments. I created the scripts. Some of these scripts I'm talking about also in later presentations. And they simulate realistic grammars. They are not empirical theories, but they simulate realistic grammars anyway. They have the same operations and some of the grammars used today, and they work with the quite realistic data segments. And I wanted to see how that type of theory, how fast the calculations are increasing. And now I must apologize that I didn't think about this. I'm sorry, I didn't think about this, that I should bring up this topic here. I just gonna quickly see if I can quickly find it and give you the numbers, what I found. Let's see if I find it here. Yes. So I'm just gonna give you the numbers from this paper, what I found when I did this experiment. So you get an idea of what kind of complexity problem what kind of complexities you will face if we work with the realistic grammar. So here are some numbers. This kind of expression, for example, the angry dog bites the man, required, this is an attested sentence, required more than 10,000 calculation steps. And then here, if I expand the sentence like, the dog bites the man in the city, the number was 650,000 steps. So you can see how fast it is growing, and how already very simple expressions require a huge amount of calculation steps. And let's take some other things also into account. First of all, these numbers are simply are for one expression. Our dataset has typically hundreds of thousands or tens of thousands. So we have to perform, let's say, 600,000 calculation steps on average for each expression. Let's also remember that when we develop scientific hypotheses, we can't assume that our first guess or first idea is always going to be jackpot. It's just a nature of human fallibility and human imperfection that we have to go through some trial and error, even if we are genius level, or even if our initial guess would be quite good. So we go through the data set with paper and pencil notebook, and we calculate 500,000 calculation steps for first expression, let's say 100 calculation steps for the second, and then third we calculate 50,000 calculation steps, and we found that, okay, that there was a mistake. The model is not working correctly. So we go to think what we change, we go to change something, and we had to start everything from the beginning, because we always have, of course, we have to check that the new model is still handling the first and second expression correctly. So each time we make a slightest change in our theory or model, we have to do all of these calculations. So how many calculation steps we are gonna write down into notebooks for any kind of interesting, realistic linguistic research project? Now, the amount of steps is too much. It's too large set. So we conclude that we are in a kind of a dead-end situation, because we introduced a methodological principle which requires us to do these calculations. Remember, it's not enough that that we believe that the model implies the data. And it's not enough that we sketch some kind of proof by looking at paper and pencil, a couple of examples, and sketch some storyboarding. So we have to actually perform all these calculations. And you have to be able to give them to me and show me that here they are, I did it, and that data was correctly calculated. So that was fine. We thought, yeah, this is good idea, but now we are in a dead end because we can't implement it. We can't do all these calculations that are required. And so what I proposed we do, and what we will now be doing in the subsequent presentations, is that we simply give up the assumptions that we do all these calculations. And we will let computers to do them instead. They are still a trivial amount of calculations for modern computers. So we will formalize our hypotheses in a language that the computer can read and understand. In this case, I use Python, but any programming language is okay here. We express the theory and our ideas in that format. And then we create a computational infrastructure, a couple of additional layers of code, which allows us to explore all the empirical consequences of that theoretical construct or that hypothesis, and match those consequences automatically with what we have in the dataset, any dataset, exactly in the way as I described. So the algorithm will just go through all possible ways of assembling expressions from the primitive elements as implied by our theory or hypothesis or grammar. And by doing so, it verifies that the hypothesis matches with reality. That's in a nutshell what we are going to do. And this presentation was just my attempt to explain why we have to use computational techniques. So, okay, but you can ask, one can, of course, in this situation, one can start thinking, well, I'm lazy. I don't want to have anything to do with programming. That's not my thing. Is there any other way that we can move forward from this point? Is there some loophole in this argument? Can we please try something else? And unfortunately, there is no way. It's not even so much the enormous combinatorial problem we are facing. Because even if the amount of calculations would be more moderate, let's say we talk about 1,000 calculation steps for one expression, it's still not feasible as a real practical research project, simply because we have so many sentences in the dataset and we have to do all these calculations so many times. So there is nothing else that we can rely on, unfortunately. So, in conclusion, when we look at linguistic phenomena and linguistic data, we quickly realize that there is a combinatorial system underlining it. Our brain is able to create complex expression by combining more simple elements, ultimately the words or whatever the most primitive elements are. And because the theory and hypothesis has to create this type of combinatorial system also, the amount of calculation and calculation steps that we have to perform to satisfy the methodological principle introduced in presentation 2 is enormous. millions and hundreds of millions of steps. And that's why we will have to begin to use computational techniques to perform all these calculations.